Welcome to our unit on radicals. We're going to be doing a lot with radicals, which are going to be square roots, cube roots, etc. This particular unit worth of material has a lot of different types of problems, a lot of different types of directions that we're going to see as we start to move throughout this unit. So my very first piece of advice before we even get started is to start developing a set of flashcards. And the way I'd suggest developing this set of flashcards is create a flashcard for each type of direction that we see. So each new direction that you see, write down the directions, the full instructions for the directions, and one example problem on one side of the flashcard. And on the other side of the flashcard, not necessarily the answer, but what steps would you go through? And in particular, what are you being asked for? What is it that you're trying to solve? So that's what we want to look for in these flashcards, because one of the tricky things throughout this entire unit is going to be all the different types of questions you're being asked and what should you do in each situation. And as you know in math, if you don't know how to start a problem, you're going to be in trouble. You can't get partial credit even if you don't know how to start it. So that's kind of the goal of the flashcards, is so that you can develop these each time that you see a new type of problem, and that way by the end of the unit you can shelf them together and study with them. Now, the other thing I want to make you aware of as far as our class in this unit is that the exam is going to be a completely no calculator exam. And this isn't to punish you, this is not to make it tricky or harder. It's actually to make it easier. Because your calculator is going to do a lot of the functions that we're going to learn how to do, and my goal here is to make sure that you understand how to do the functions. So if I allowed you to use your calculator, I'd have to write more challenging problems that involve a lot of variables, and this way I can actually test that you're knowing how to do the process. By making it no calculator, I can ask easier questions where the focus isn't so much on making it complicated. It's just saying, hey, do you got the basic principles of what you're supposed to be looking for here? Now, that does mean that we will have some calculations, some basic calculations to do without a calculator. So the handout that you should have already had, and that's up here on the screen, are going to be all the powers that I expect you to know without a calculator. The shaded out portion is when the numbers get too big and I wouldn't expect you to know them. And so the first column is your squares, your second powers. And I expect you to know up to at least 13. You should probably know a couple more than that. But these are ones that are basic multiplication facts you should just basically have memorized. Now, as far as the cubes, I expect you to recognize these and be able to quickly come up with them. And so something I want to point out about cubes, and really the powers in general, is let's start off by looking at 2 cubed. 1 cubed is a little bit obvious. I want to point out that it should be easy to get 2 cubed if you already know 2 squared. If we know that 2 squared is 4, then 2 cubed, which is 2 times 2 times 2, would just be 2 squared times another 2. So that means 2 cubed is just 4 times 2. So if we know what the square is, we know what the previous one is, we're just going to say multiply by 2 one more time. If we move on to 2 to the 4th power, we can use basically the same reasoning. We can say 2 to the 4th power is going to come about from doing 2 cubed, and then multiply one more 2 in there. So that would be 8 times 2. And similarly then, if we want to look at 2 to the 5th. 2 to the 5th, we could say, take my previous answer from 2 to the 4th and multiply by one more 2. So each step over we take, we're just saying multiply by 2 one more time. 16 times 2 is 32. And we can do the same thing then for the 3 to a powers. As we look across this one, we know 3 squared is 9. 3 cubed is to take that answer of 9 and multiply by 3 one more time. That gets us 27. Now we could do the same thing for 3 to the 4th, but I want to point out something else about 3 to the 4th that might be helpful. 3 to the 4th is just 3 squared squared. And if we know that 3 squared is 9, it's just 9 times 9. And that's 81. So that's another way to look at it, just so that you kind of know it. As we look over towards the 3 to the 5th power, multiplying 81 by 3 shouldn't be hard, because 3 times 8 gets us 24. 3 times 1 gets us 3. So 24, then 3. 243. So that one shouldn't be too bad. Now as we look at our 4 to a powers, we know 4 squared is 16. So if I'm going to do 4 cubed, I'm going to multiply by 4 one more time. Now I want to talk about that. So if we're looking at 4 cubed, and we know that that's 4 squared times 4, or 16 times 4, the way that I like to think about multiplying by 4s is to think about doubling twice. 4 is 2 times 2. So if I take 16 and I double it once, I get 32. If I double it again, I get 64. So multiplying by 4 is to double twice. If we then look at the 4 to the fourths, if I double 64, I get 128. Double it again, I get 256. Now, if you want to start looking at the 5s, if I were you, I'd think about money. 5 squared is 25. So let me come over here. So that means 5 cubed would be 25 times 5. I think about this in terms of money by saying, what if I had 5 quarters? If I had 5 quarters, how much money do I have? Well, 4 of them make $1. You get $1.25. And now we can say, well, if I want to go up to 5 to the fourth, I'm going to multiply this by 5. And so that means I've got $5 bills with an additional quarter on each. So if I have $5 bills, and then I got another dollar from those 4 quarters, that's $6, and there's still 1 quarter left, so it's $6.25. And that is 5 to the fourth is 625. So these are all values I expect you to know or be able to quickly determine without a calculator. All right, so now let's get into some definitions. That's what really this lesson is going to be about, is our definitions and rules that are going to surround these radicals, these square roots, these cube roots, etc. So we're going to first of all define what a square root is. And you can see on the screen we're saying to find the square root of a number a, we find a number that was squared to get to a. That's our basic idea. So if I want to talk about 5 squared, knowing that that's 25, I could also say negative 5 squared is 25. So does that kind of mean that 5 and negative 5 are both square roots of 25? Yes, in terms of a definition of the word square root, yes. But please notice the detail I put into that. The word square root, yes, 5 and negative 5 are both square roots of this. But that creates a problem. In math, we like to make sure that when we're given a problem, we get one answer when we're given an operation. An operation having only one answer is what we call a function. And we'd like for this square root idea to be a function, to say, you give me something to take the square root of, and I give you one answer. I don't want to be able to say, take the square root of 25 and get two answers of 5 and negative 5. So the symbol that we're used to associating with the square root, that funky looking checkmarky thing, that's actually what we call the principal square root. And the principal square root, another word for that, is the positive square root. So what we want to look at here is to say, if I have that symbol, square root 25, I'm asking for the positive answer. What positive number multiplied by itself equals 25? Now, if we have a negative sign in front of it, well, what that kind of means to us is if I was only looking at the square root of 25, that would be 5, but then the negative sign copies down, and so I get negative 5. So if I have a negative in front of my square root, then that means get the positive answer and then take the opposite of it, and you'll end up with a negative answer. So that's what's going on. That's kind of our basic definition of the square root. And so let's go ahead and look at some examples of applying this and determining square roots. So let's look at some examples of these square roots. The directions that you'd expect to see on a problem like this is simplify the following square roots or simplify the square root. So the first problem here is square root 36. We're just being asked, what number times itself equals 36? And so our answer here would be 6. Now, one of the things that you want to kind of think about when you're looking at any sort of new mathematical idea that you're studying is to say, what happens when I look at positives? What happens when I look at negatives? What happens when I look at zero? What happens when I look at fractions? And so that's really what we're going to look at here in these next couple examples. We're going to try to hit on each of those different topics to say, how does this behave with zero? Can I take the square root of zero? Is there a number that when I multiply by itself it equals zero? Sure, 0. 0 times 0 does get me 0, so taking the square root of 0 is a perfectly well-defined value. Now for C, if I want to think about multiplying something by itself to get this fraction 4/49ths, I got to think about how I multiply fractions. That if I have a fraction times a fraction, I just multiply across the top and multiply across the bottom. And so what that tells me then is that I can simply take the square root of the top and the square root of the bottom separately and get an answer of 2/7. Because if I would have multiplied 2/7 times itself, I would do 2 times 2 and 7 times 7. So taking the square root of 4/49ths does in fact get me 2/7. Now I want to look at D and E here at the same time. These are two very different problems that are asking two very different things. And so I want to identify what's going on here. Now example D here, the part D, is kind of like what we were looking at in the intro to this example to say, I can take the square root of 81, like if this negative sign wasn't there, I can take the square root of 81, and that's a 9. And then that negative is really saying multiply your answer by -1. And so if my answer was 9 and I multiply it by -1, I get -9. Perfectly fine answer. Now, E, on the other hand, is asking a different question. This is saying, I need a number that when I multiply it by itself, the answer is -81. Well, if I were to multiply a positive and a positive together, the answer would be positive, so it can't be that. What if I multiplied a negative and a negative together? Well, the answer is also positive. So I can't multiply a number by itself to get a negative answer, at least not a real number. And so that's actually how we want to answer this, is not a real number. Let's actually write number in there. We're not going to say no solution, because we're going to learn later in this unit, there is a solution. There is something this simplifies down to. It's just not a real number. It's what we call an imaginary number. We're going to define what that is and how to find it a little later on, a few more lessons from now. But for now, we're just going to say, hey, it's not a real number. So we define a square root as a number that when you multiply it by itself, you equal the number you're trying to take the square root of. So the square root of a number is what number multiplied by itself equals this. Now we can extend that idea beyond squares and talk about cube roots. So a cube root, which has this little index up here of a 3, this is called the index of the radical. That index of 3 is saying, let's take the cubed root, which is to say, what number cubed equals this? Or in other words, what number times itself 3 times equals this number? That's how we're going to define a cube root. Let's look at some examples of those. So let's look at some examples of finding cube roots. The first question is to find the cube root of 8, which is to say what number times itself 3 times, or what number to the third power equals 8. So let's go ahead and write that out. We're saying what number cubed equals 8. This is what we're asking. Now if you go back to your powers chart, it might be helpful, because you should be able to look right at this powers chart and say, what number cubed equals 8? Well, 2 cubed equals 8. So I can come right back to this example and say 2 cubed equals 8, which means the cube root of 8 is 2. Now let's look at B. Cubed root of negative 64. Now if you remember back to example 1, when we took the square root of a negative, we said that's not a real number. But our reasoning for that is because if you multiply a positive and a positive, you get a negative, or at least you get a positive. If you multiply a negative and a negative, you also get a positive. There's no way to square a real number and get a negative. Let's see if that same reasoning applies for a cube root. What happens when we cube a negative? Well, the answer is actually negative. So it looks like we actually can take the cube root of a negative number. And so again, this question is then saying what number cubed equals negative 64? And we know this is going to end up being a negative number on the inside. And so really we need to say what number cubed equals 64, the positive version, and then we'll notice put a negative in front of it. And so we can again come back over here to our handy dandy chart. Since we're looking for something cubed, we know that all we got to look at is the cube column here. And we're trying to equal 64. And so we find 64 over here, and the number in question is 4. So if we come back over here, the number in question is 4. Negative 4 cubed would equal negative 64. And so that's our answer to this problem, is negative 4. Now we can actually extend the idea of the square root and the cube root to any power that we want. So we can talk about fourth roots and fifth roots and sixth roots and seventh roots. And they have the definition that you'd expect. A fourth root is to say what number to the fourth power equals me. A fifth root is going to say what number to the fifth power equals me. And so as we increase this root to talk about fourth, fifth, and sixth, we're basically just going to be looking at the index, and we're going to change that index to whatever root it is that we're talking about. So as we're looking at this, we just really want to pay attention to the fact that if there is not an index listed, we assume it's the square root. And this is kind of similar to coefficients. If you don't have a coefficient in front of an x, you assume it's 1 times it. If you don't have an exponent on an x, you assume it means an exponent of 1. It means that we're only raised to the first power. We have a lot of assumptions like that in math, and square roots is one of those. If you don't specifically write the index, you're just going to say, let's take the most common one that we always use, square root. But if we do write an index, let's make it something special. Let's actually write it. Now, with that said, we got to be careful on how we write things as far as on paper. When you're writing a fourth root, make sure it's clear that that 4 is there. We don't want to say for this. This isn't clear if that's a fourth root or 4 times the square root. So as you're writing this, you want to get in the practice of basically looking at this table that your index is sitting on. Your index needs to sit on that table of your square root or of your radical symbol. And that way it's clear that that's your index. Let's work through a few more examples. The first example is the fourth root of 81. So in this question, what we're really asking for is we're saying, what number to the fourth power equals 81? And so again, if we come back over here to our power chart, we know that we're talking about a fourth power. So we're only looking at this column here, and we're looking to equal 81. So we can hopefully very easily see that the number in question is 3. 3 to the fourth power equals 81, meaning my answer is 3. Now as far as example B, we're looking at the fifth root of negative 243. So we got a negative here again, and so we got to take a step back and say, are we allowed to do this? Since the index is odd, it's okay. We can take the radical of a negative number if the index is odd, because we saw with the cubed root that a negative times a negative times a negative, an odd number of times, equaled a negative. Whereas when we talked about the square root, if I have an even number of negatives, the final answer is going to be positive. It's never going to be negative. So we can actually do this problem, is the point, to say there does exist a number that when I raise it to the fifth power, the answer is negative 243. And I know that number is going to be negative. So really, I want to focus on something to the fifth power that is 243. So I'm going to come back over to my power chart. I'm talking about fifth powers, so I'm only looking at the fifth powers. And 243 is the magic number I was asking about. And so it looks like 3 is what we are raising to the fifth power. Now, obviously, it's negative 3 since we're getting a negative answer, but that's our answer then, negative 3. Now, for example, C here, we have an even index. So that means I'm multiplying something by itself 4 times and supposedly equaling a negative. That can't happen. If we're multiplying an even number of times, we're going to get a positive no matter what. So this is another example of not real because the index was even. Now for the last example, we're looking at a sixth root. So we're asking what to the sixth power equals 64. Now again, we can go back to our little chart. This is very handy. You should bring this with you to class every day, this chart, and you should have it in front of you while you're doing your work. Come test time, you should be able to create this chart. You're not going to have it in front of you on the test, but you could have a scrap sheet of paper and write it as the very first thing you do. So remember, our question that we were looking at was a sixth power, and we wanted to equal 64. So it must have been 2 to the sixth. So that means our answer here is 2. All right, let's talk about a really interesting topic that can sort of be tricky for some people. So let's try to work our way through it though. What we'd like to be able to do is we'd like to be able to figure out what the square root of x squared is. So really what we're being asked here is what squared equals x squared? Well, quite frankly, it seems like it's a pretty easy answer there. It seems like the answer here should probably be x. X squared would equal x squared, right? Well, actually not quite. And we're going to see why and why it's tricky, but we kind of got to think back to something I said previously, that when we're approached with a new mathematical idea, one of the things that I want you to think about is what happens when we use positive numbers, what happens when we use negative numbers, and what happens when we use 0. Sometimes fractions mess things up too. But you want to look at all those situations. So let's first of all start off with some positives. Let's look at the square root of 3 squared, 5 squared, 7 squared, and 23 squared. Those are all of the form square root of x squared. Now, if it was true that the square root of x squared is x, then my answers here would be 3, 5, 7, and 23, because that's what it is that we're squaring. So in the first example, 3 squared is 9, so square root of 9, well, that really is 3. 5 squared is 25, the square root of 25 really is 5. 7 squared is 49, the square root of 49 really is 7. So, well, 23 squared, big number. Square root of it, well, it really is 23. So our answers of 3, 5, 7, and 23 that we are hoping really are the case. So far it actually looks like it is true that the square root of x squared is x, so far. This seems to be true if the x's that we pick are positive. So far that's what we know. If we pick some positive x's, then the square root of that squared is itself. But let's look at what happens when we pick some negatives. If it were true that the square root of x squared is x, then the answers we'd expect are negative 2, negative 4, negative 5, and negative 23. If I look at that and say, all right, well, this is what it would be if it was true that x square root of x squared is x, it's the thing I'm squaring, well, that can't be the answer. Because I'm taking a square root of something, I know that the answer to a square root needs to be positive. So those can't be the answers, which tells me it isn't true that, it isn't true that the square root of x squared is x. Let's look at what actually does happen when we try to solve these problems to understand what the answer should be. So if I take negative 2 and square it, negative 2 times negative 2 is positive 4. I get the square root of 4. The answer to that is positive 2. If I square negative 4, I get 16. The square root of that is 4. And if I continue on, I get the square root of 25, which is 5. And you could probably guess then for this last one that the answer is actually positive 23. So if we look at what's happening, when we squared our number, we actually lost information. When I got my answers of 4, 16, and 25, I don't know if I had squared positive 2 or negative 2. I don't know if I squared negative 4 or positive 4. So if I just told you I squared a number and the answer was 16, you don't know if I squared 4 or negative 4. But once I take the square root, the answer is positive. So what's happening here is we're getting the positive answer no matter what. So if I square a number, then take the square root, the answer I get is positive no matter what. Do we have a mathematical way of saying that? Do we have a mathematical way of saying, make my answer positive? Because what we wanted to say is we wanted to say the square root of x squared is x, but we want to say the positive version of x. We do have a way of saying the positive version of x. It's the absolute value of x. So that's really what the rule is. And the same rule applies if I wanted to take the fourth root of x to the fourth. That would also be the absolute value of x. Or if I wanted to take the sixth root of of x to the sixth, that would also be the absolute value of x. Is that true for the cubed root of x cubed, though? No. Because if I plug in a negative number and cube it, the answer is negative. I didn't lose any information. I know that it came from a negative number. When I take the cubed root, I stay negative. So in the case of the cubed root of x cubed, it really is just x, no absolute value needed. And so what that tells us is that if we're talking about an even number, that we take the nth root of x to the n, then we need an absolute value. We need to say your final answer is positive no matter what. Whereas if that number of our index, that n, is odd, then we're allowed negative numbers. So the answer is just x. The nth root of x to the n really is just x. So let's look at a couple examples here that are going to utilize this idea. So let's take the square root of x to the sixth. It's going to utilize this idea, even though it's not exactly an application of it quite yet. But if I'm asking you for the square root of x to the sixth, what I'm asking you for is I'm saying, what number squared gets me x to the sixth? That's what the square root is asking. Well, x cubed squared would get me x to the sixth. So really this question could be rewritten, if it helps you, in this way. The square root of x cubed squared. X cubed squared is x to the sixth. And now I have the square root of a square, and so I know that the answer to that is the absolute value of whatever it is that I'm squaring. So my actual answer to this problem is the absolute value of x cubed. Whereas the cube root problem, we don't have to worry about the absolute value. This problem is saying, what number to the third power gets me x to the ninth? Well, that would be x cubed. Remember that when you raise a power to a power, you multiply the powers. 3 times 3 gets you 9. So this tells me my answer is x cubed. No absolute values are necessary. All right, I want to ask you a couple of questions that I hope to be ridiculously simple. What is the absolute value of 5? Well, if you remember, absolute value basically means make it positive. The actual definition is your distance from 0 on the number line. But it basically means make it positive. So if you take 5, which is a positive number, and you make it positive, well, the answer there is 5. Woohoo! We're geniuses. What's the absolute value of 9? Well, let's take 9 and make it positive. 9! How about the absolute value of 15? 15! Yay! Pretty easy. If you already have a positive number and you take the absolute value, those absolute value bars are redundant. They're not doing anything. If I say take 5 and make it positive, you don't do anything. So why write the absolute value bars in the first place? We wouldn't. Not as a final answer, anyhow. So if you got a final answer of 5 that I said, hey, will you do me a favor and add 4 plus 1? You're not going to write that as the absolute value of 5. That'd be silly. Instead, if I said what's 4 plus 1, you would just say 5. So we're not going to put an absolute value in our final answer if we automatically know it's positive anyhow. That wouldn't make any sense at all. Let's think about that as we look at these next examples. So let's take a look here at example 5. What I want you to notice is that there's two separate sets of directions for the same problems. And this is really important, and this gets back to a note that I made at the beginning of this lesson where I talked about making sure to make flashcards for different directions so you understand what you're being asked for. So both of these sets of directions start off, find the following radicals. The first line says assume that variables represent positive real numbers, whereas the second line says assume variables represent any real number. So square root of x to the 6. We actually did that example a little while back, and we found that the answer to this was the absolute value of x cubed. But let's look back to the bold directions. The bold directions say assume variables represent positive real numbers. So our x is representing positive numbers. Do we really need the absolute value bar there? No. That gets back to what we were talking about in the intro to this example, to say if you have the absolute value of a positive number, you don't need the absolute value bars. You know that it's positive, and so there's no need to say make it positive. So if we have these special directions that specify your variables are positive numbers anyhow, then we don't need the absolute value bars. So for the cubed root of x to the 5th, we can say what to the 3rd power equals x to the 15th? Well, that'd be x to the 5th. That's a cube root, so we wouldn't need absolute value bars anyhow. Now how about the square root of 9x to the 4th? Well, the square root of 9 is 3. The square root of x to the 4th is x squared. And we don't really need the absolute value bars, because again, we already know the x is going to be positive. Next example, the 5th root. Well, the 5th root here is odd, and so regardless, we wouldn't have absolute values. Oops. Hold on a second. Sorry, I'm jumping around there. My fingers are hitting the wrong thing. 5th root of 32 is 2. 5th root of x to the 15th is x cubed. And that would be the answer. Now let's take a step down where we assume variables represent any real number at all. This is where sometimes we will need the absolute values. So in the first example, this is the same example that we did see earlier, that we know that we should have the absolute values. But with cubed roots being an odd index, we don't need the absolute value because it's odd. Now for the next one, the square root of 9x squared, this one's a little bit tricky. On first glance, it looks like we need absolute value bars because we're taking a square root, which is even. But let's look at x squared. If you take x squared x squared is always going to result in a positive number no matter what. And so realistically in this case, we could ignore the absolute values as well. Our last one is an odd index. So there's some examples, and pay very close attention to the different directions. That if we specify that our variables are positive, we'll never need an absolute value because everything's positive already. We don't need to say make it positive. But if our variables could represent any real number, that's when we have to be careful about the absolute values. Now, so far, each of the numbers that we've been taking square roots of have been perfect squares, which is kind of nice then. We can take the square root of 36, of 25, of 49. All those numbers get nice, happy, whole numbers. But what if you're taking the square root of a number that's not a perfect square, like the square root of 3? Well, when you're talking about the square root of 3, we really don't know exactly what it is off the top of our head, so we got to use a calculator. Now, our exam is going to be no calculator, but you still will have some homework problems that will involve a calculator. For instance, find things like square root 3. And one of the things I do want to point out about the square root of 3, depending on your calculator, if you're using the TI-30XS Multiview, the scientific calculator, if you're in math print mode, which I encourage you to be in, then when you type in the square root of 3 and hit enter, the answer that it gives you is going to be square root of 3, which isn't exactly helpful. What we're looking for is a decimal approximation here. So the button that's right above enter that has an arrow to the left and arrow to the right, what that button does is that button converts between math print mode, where your answers display as mathematical notation, and what's called classic mode, or where answers display as decimals. So if you just hit that button, it'll go ahead and display the decimal approximation to anything that is normally giving you some sort of math print on. So please be aware of that button. It's a very helpful button when you're using that scientific calculator. Okay, so let's go ahead and look at that square root of 3. So if we put in square root of 3 into our calculator, we get some sort of answer, and we can round this to however many decimal places we want. I'm going to call it 1.73. Oops, let me use ink instead of highlighter there. Sorry about that. We're going to call this 1.73. But as I've said before, our exam is going to be no calculator. So let's look at, does this make sense? So if I didn't have a calculator, I want to get a ballpark idea of what this should be. Does 1.73 make sense without a calculator? And so as you can see below, what I've done is I've set up a little compound inequality to help us determine if this makes sense by saying what two perfect squares is 3 in between? 3 is bigger than 1 but smaller than 4, where 1 and 4 are perfect squares. So that means if I took the square root of 1, that'd be 1. If I took the square root of 4, it would be 2. So I know that the square root of 3 is somewhere between 1 and 2. I don't know exactly where, but I am a little bit closer to 4 than I am to 1, so it's probably closer to 2 than it is to 1. And so sure enough, it is. 1.73 is a little closer to 2 than it is to 1. So it does make sense that our answer is about 1.73. Now I want you to think about that so you can get kind of ballpark ideas. And this is important for when we do start putting stuff into the calculator, because sometimes we type stuff wrong. And if you type it wrong, you should kind of know ahead of time roughly what your answer should be. Let's shift gears a little bit to talk about graphing when it comes to these radical functions. So some of these we already know. We already know how to graph f of x equals square root of x. We saw that early on in the course. This is one of our functions that we basically had memorized. And so remember, the basic look of the function is the top half of a sideways parabola, and our x values came from 1, 4, and 9 for each step up that we take. So if you remember, you start off at 0, 0. If you take one step up, then you need to take a step over from 0, 0. If you take another step up, then you take 4 steps over from 0, 0. And if you take another step up, then you take 9 steps over from 0, 0. And so if we connect the dots, we get ourselves this graph. Now I do want to remind you, there is an arrow over here pointed to the right, and it's also going up at the same time. But over on the left, this is a closed-in circle over here at the origin. We don't have values further to the left, and that's because we can't take the square root of a negative number. There's also no values lower than that, and that's because our answer can't be negative. We can't take the square root and get a negative answer. Now, hopefully you remember these terms from your prerequisite course, domain and range. Your domain for any given function are all of the allowable x values that you can plug in. The range is all the allowable y values that might come out as an answer. So on this particular function, our domain, our x values, is that we need to make sure that what we're plugging into our function is bigger than or equal to 0. In terms of interval notation, we can include 0 and anything to the right. So that's the domain for this. Now we can actually visualize that domain as well. And let me explain how to visualize that domain. Let me just erase my highlighter marks off of here. If you want to visualize your domain, then picture yourself scanning your graph from left to right. So I've got this scanner where this yellow bar is what I'm scanning. And I'm going to take that yellow bar and say, hey, do I have any x values here? Nope. Let me keep moving it over. Let me move it over. Let me move it over. Oh, I hit an x value. I have an x value as early as 0. My scanner keeps scanning. I'm scanning, I'm still getting x values. I'm still getting x values. And as far as I go over, I'm going to continue getting x values forever and ever and ever. So the first x value that I got was 0, and I included it. And I kept getting x values on to infinity. And so my interval notation for that is from 0 to infinity. Now the range is the allowable y values. I can similarly kind of scan my graph and say, hey, let me scan down here. Do I have any values on my graph? No, not yet. Let me take a step up. Let me keep on scanning. No values yet. Oh, there's a value. I have a value as early as 0. And as I keep scanning up, I keep hitting values, hitting values, hitting values. And even though on my graph that's visually here, I'm not getting values up high, the graph is still increasing. So I am eventually going to hit a value, so it's going to be really far to the right. The very first y value that I had was 0, and I kept on going up. So I went up to infinity. That's the range on the square root. Let's talk about the cube root. Well, this is a new graph that we haven't seen before, so when we see a new graph, we're always going to pick some x's, plug them in, and see what we get. If I plug in 0, the cube root of 0 is 0. The cube root of 1 is 1. Now we're not going to plug in 2 because I don't know what the cube root of 2 is. So I want to look back to my square root and say, why did I pick 1, 4, and 9 for my x values? Because those were perfect squares. So if I'm trying to do a cube root, let me pick perfect cubes. So that would be 8 and 27. Give me y values of 2 and 3. Now with square roots, I could not plug negative numbers in. With cube roots, I can. So I could actually plug in -1, -8, and -27 as well, giving me y values of -1, -2, and -3. So if I plot these ordered pairs, now I don't have room to put 27, 3 on my graph, but I kind of get an idea that this particular graph is getting really shallow, because if I sort of aim at 27, 3, it's going to make my graph pretty flat. So over here, I'm getting pretty flat afterwards, and the same thing's going to happen in the negative direction. It's going to be pretty flat. So this is what the cube root graph looks like. Now, as far as my domain and range, what x values do I hit on this, or what x values am I allowed to plug in? Well, anything I want. This graph keeps going to the left and it keeps going to the right. I'm allowed to take the cube root of anything. And what y values do I hit? Well, I eventually hit everything because this graph continues to go down and it continues to go up over there. Not very quickly, but it does continue to go down and continue to go up, meaning that my range is also negative infinity to infinity. So with cube root graphs, your domain's always going to be negative infinity to infinity. Your range is always negative infinity to infinity. But with square roots, we do have a restricted domain and a restricted range. So let's look at a couple graphs that have been shifted and look at their domain and range. So the first one is the square root of x plus 2. So if we go all the way back to the first unit that we covered, we know that this shift is a shift to the left by 2 units. So if I were to do a quick sketch of this, the graph of it would look something like that. So if you're being asked for the domain and range of this, the domain, or all the x values, is the leftmost x value that we ever hit is negative 2. The rightmost, well, it keeps going to the right to infinity. As far as the range, or the y values, the lowest y value we have is 0. And this guy keeps going up. Now the domain we could have actually solved algebraically as well, because we know that what we're taking the square root of, the x plus 2, we know that it needs to be greater than or equal to 0. So if we solve that for x, we find x needs to be greater than or equal to negative 2. Let's take a look at the second example. Square root of x and then plus 2. If we go back to our shifts, this is a shift up by 2 units. So if we do a quick sketch of this, it's a square root that starts there. So as far as the domain, or all the allowable x values, the leftmost x value that we see is 0, and it continues going to the right. But as far as the y values are concerned, the smallest y value that we have is a y value of 2. But it does keep increasing after that. Now as far as cube roots, remember that every cubed root, your domain is everything, your range is everything. I don't care about the shifts. Now yes, I could do the shifts on this one, and if I were to do a rough sketch, this would be to the left by 2 and up by 5. So that's my middle point, meaning I go upright and down left from there. So that's roughly what this guy would look like if I was graphing him, and I could get the actual ordered pairs using 1, 8, 27. But most importantly is this rough idea, and then there's your domain and range. All right, we're going to go ahead and change gears to talk about a new definition or rule as we progress through this lesson. In this part of the video right now, we want to develop a rule. So it's not so much that we're solving the equation in front of you here, it's that I want you to understand where a particular rule or definition comes from. So let's just go ahead and say I asked you to solve x cubed equals 5. Now, what I'm really saying then is I'm saying what to the third power equals 5. And that's really how we define the cube root. The cube root was to say what to the third power equals this. So in this example, the x value that I'm asking you to solve for, by definition, is cube root 5. That's how we define the cube root. What if, instead of using that definition, what if I wanted to say, let's undo the third power? If I could multiply the third power by 1/3, that would undo it. So if I could raise both sides to the 1/3 power, that would undo the third power, and it's true, it would. So as I'm looking over here at the left-hand side, if I have x cubed to the 1/3 power, when you raise a power to a power, you multiply the powers. 3 times 1/3 is 1. So that means this is x to the first power. So by raising both sides to the 1/3 power, I'm able to find that in this case x is 5 to the 1/3 power. So I solved the same equation in two different ways. In one way I got cube root 5, and the other way I got 5 to the 1/3 power. Those two things must be equal because we are solving an equation. We're not going to get two different answers. The answer is going to be the equivalent. So that means 5 to the 1/3 power is equivalent to the cube root of 5. And so really in general, it's true that the 1/3 power is always going to mean the cube root. The 1/4 power is going to mean the fourth root. The 1/5 power means the fifth root. So if I have x to the 1/2 power, that's the square root of x. If I have x to the 1/3 power, that's the cube root of x. If I have x to the 1/4 power, that's the fourth root of x. If I have x to the 1/5 power, that's the fifth root of x. I hope you get the idea. And so where we're going with this is we're going to progress through some definitions of what fraction exponents actually mean. Up to this point, when it came to exponents, we've really only talked about positive and negative exponents and zero. So now we're going to talk about fraction exponents and what they mean. And so we're getting a definition here for 1 over something as an exponent means that denominator is the index of a radical. That's what's going on here. So let's do some examples. Directions here, and make a new flashcard. Use radical notation to rewrite and simplify the following. 4 to the 1/2. So that 1/2, remember, means square root. So this problem is really just saying square root of 4. Square root of 4 is 2. That's easy. Second example, the 1/3 power. The 1/3 power means cube root. So this problem is asking for the cube root of 64. If you go back to your powers chart, you'll find that that's 4. Now, this next one is tricky. So let me talk about this one real quick, and let's talk about this in a simpler sense. Let's ignore the fraction exponent for a second. Let me remind you of something that you've learned about previously. Let's talk about the difference between -2 squared and -2 squared. Those two things look very similar, but different answers. And those different answers come about because of order of operations. The first one, -2 in parentheses squared, is saying -2 times -2, and a negative times a negative is a positive. Whereas the second example, remember that a negative sign really means -1 times whatever it is. And so what this is saying then is order of operations, PEMDAS, please excuse my dear Aunt Sally. There's no parentheses here, but the next thing I should do is exponents. 2 squared is 4. Then do my multiplication. So that one's -4. The negative outside happens after the squaring. The squaring happens first, then we apply the negative. And so really the same thing needs to apply on example C. This is really saying -1 times 9 to the 1/2 power, or -1 times the square root of 9, or -1 times 3, or -3. That's really what this is saying, is take the negative after handling the exponent. Whereas I know this problem isn't asked right here, but if I had asked for -9 to the 1/2, where the -9 is in parentheses, that would mean take the square root of the whole thing, which at that point we're going to say not real. Now I know that wasn't asked, but just so you're aware, that's what it would look like if we were to get a not real value there. On to example D. The 1/4 power means the fourth root. We have 81 x to the 8th. The fourth root of 81 is 3. The fourth root of x to the 8th is x squared. Now, we can also use these exponents to help us understand how quickly I can be able to get x squared there, because let's look at just the fourth root of x to the eighth. Well, what that means is x to the eighth raised to the 1/4 power. And when you raise a power to a power, you multiply their powers. And what's 8 divided by 4? Well, it's 2. And so we can actually see that there's a rule developing here, that when you have x to a power and you're taking a radical of it, you can basically just take the power and divide by the index. And that's because of this rule, because of what's going on with these rational exponents. And there's the fancy name for what's going on here, that fraction exponents are called rational exponents. Rational, remember in math, means like a fraction. Because when we look at the word rational, the first 5 letters are ratio. Ratio means fraction. The null part of rational means like a. So rational means like a fraction. So rational exponents are fraction-like exponents. Now, in the last example, we looked at having an exponent that was 1 over something. And we said that something becomes the index of the radical. But what if instead of having 1/2, 1/3, 1/4, 1/5, what if we had something other than 1 in the numerator? Well, let's look at what that means. If you have m over n as your fraction, you could write that in one of two ways. You could write that as the base to the m power, and then raise that to the 1 over n. Or you could take your base to the 1 over n power, and then raise that to the m power. And either way we do this, we're saying m times 1 over n is how I get m over n. And it doesn't matter which order I multiply in. Now, in terms of radicals, remember that the 1 over n power means the nth root. So the ways that we can write a to the m over n is we can either say take the nth root of a to the m, or the nth root of a, and raise that to the m. Either way. Now that, of course, does beg the question, which one should you do? Should you take the radical and then raise it to the power, or should you raise it to the power and then the radical? Now, the big answer here, now, you can see that the one with parentheses looks a little bit messier, but if you take the radical first, you're making it smaller first. Then you raise it to a power, you're making it bigger. So when we're dealing with numbers, not variables, I would take the radical first. Make your numbers smaller before you make them bigger. So given the choice between raising something to a power or taking a radical, if we're dealing with numbers, let's take the radical first because we're making our numbers smaller. Whereas if we raise it to a power first, now we've got a huge number. Now, if we're dealing with variables, you can write it either way, but quite frankly, if you're dealing with variables, the middle way over here looks a little prettier. So that's usually how we're going to write it when it comes to variables. Big picture though, the important thing that I want you to get out of this so far is that if we have a fraction exponent, m over n, the top is the power that we're raising to. The bottom is the index of our radical. That's the big deal so far. Either order you do it in doesn't matter, but the denominator tells you the index of the radical you're taking. The numerator, the top, tells you the power you're raising to. And the easy way to remember this is to think about what's new. We've always done x squared before. X squared as a fraction is 2 over 1. The 2 is the power we're raising to. Whereas, what's the new thing going on in this whole lesson? It's when we have denominators. So once we have a denominator, that's the new thing, that's the radical. So that's how I would remember it if I were you. So let's look at a couple examples. Now our directions here are going to be something along the lines of simplify the rational exponent, something like that. But I want you to notice about this problem, though, is that we have numerical values that we're raising to numerical exponents. Our final answer should be a pretty straightforward, simple number. So for the first example of 16 to the 3/4, we need to identify what's going on. that our exponent is 3/4, meaning that the 3 is the power I'm raising to, and 4 is the index of my radical. So we're going to be taking a fourth root of this number 16, and we're going to raise it to the third power. And so again, we were talking about this before the example, that we should take the radical first, then the power, because we don't make our numbers small before we make them big. Without a calculator, I don't want to try to do 16 to the third power. That's ridiculous. Even though I could mathematically, it's correct to do that. I would rather say the fourth root of 16, that's 2. And then 2 to the third power, that's 8. That's our answer to 16 to the 3/4 power, is 8. Now if we apply the same thing over on the other problem, the negative 27 to the 2/3, we look at the exponent of 2/3. 2 is the power I'm going to raise to. 3 is the index of the radical. So 3 is the index of the radical that I'm taking the cube root of negative 27. And whatever answer I get, I'm going to square it. So my answer to the cube root of negative 27 is negative 3. If I take negative 3 and square it, I get positive 9, because again, this is negative 3 times negative 3, and this is where our organization is really important. We organize step by step by step with parentheses where necessary. So let's look at if we are dealing with variables. So if I have x to the 3/5 power, where my exponent is 3/5, I know that 3 is my power, 5 is my index. If I want to rewrite this, it looks a little bit nicer when I have the fifth root to just put the cube directly on the x. That's how we're going to write it when it comes to writing in radical form. And so again, down here in the summary area is what I've said a few times before, and it's so important. When we have a fraction exponent, the denominator is the index to the radical. The numerator is the power we're raising to. That's the biggest thing that you got to know. Now we have one last thing that might complicate our rational exponents, our fraction-like exponents. And that's if there's a negative also in that exponent. So I want you to remember that x to the negative first means the same thing as 1 over x. So a negative exponent means to take the reciprocal of the base. And this is really important. We don't want to memorize this as just saying take the reciprocal, because there's lots of things we can take the reciprocal of. Or taking the reciprocal of the exponent, or taking the reciprocal of the base. It's important to say that when I'm raising a base to a power, that what I'm taking the reciprocal of is that base. So in our simple definition here, the base is x, the power is negative 1. We're taking the reciprocal of x, so it becomes 1 over x. So let's do an example. 16 to the negative 5/4. Now off to this side, let's go ahead and talk about this exponent of negative 5/4. 5 is the power I'm raising to. 4 is the index of the radical. And the fact that we have a negative in there says we're going to take the reciprocal of the base. So our base is 16. We're going to take the reciprocal of that base. Now we're going to apply the 5/4 power by saying the index of my radical is 4. The power I'm raising to is 5. Now this radical and power can be applied to the 1 as well, but 1 taken to any radical is still 1. 1 raised to any power is still 1. So let's focus on the bottom. Now, each step that I write, I'm going to rewrite the entire step. So it's important to maintain the 1 over. The fourth root of 16 is 2. 2 to the fifth power is 32. Both those numbers come from your power chart. And that's our answer, is 1 over 32. So now we've talked about these rational exponents. And we said that the numerator is the power we're raising to, the denominator is the index, and if there's a negative, that's the reciprocal of the base. So we're going to do a refresher now of all the different rules of exponents that you've seen before, because we're going to be applying those just like you'd have in previous courses, only now we're going to say, hey, fractions are okay. Maybe we'll have fractions. So I'm going to go ahead and remind you of the rules, but also remind you why they're the case. So the first rule that we're going to talk about is the product rule. The product rule says if I have x to a power times x to a power, where those bases are the same, then I can add the powers together. Now the bases being the same are really important. Now this rule comes from as simple as saying, if I have x squared times x cubed, what does that mean? Well, x squared is xx, x cubed is xxx, so I've got 5 x's. That's x to the fifth. I'm counting them. It's all I'm doing is counting how many x's I got. So it's as simple as that. Now, one thing I do want to point out about this particular rule, some people make mistakes with this rule and they think maybe it's a times b. If you want to remember this rule, think about a nice simple example that you know the answer to. X times x. We know that x times x is x squared. But that was x to the first times x to the first. So how did I come up with that exponent of 2? Did I come up with it from 1 plus 1? Or did I come up with it from 1 times 1? And of course I came up with it with 1 plus 1, and we got 2. And that's true a lot of places in math. If you're not sure on a particular rule, think about a simple case that you know the answer to and test it. See if it works. Now the next rule is the power rule. The power rule says if I have x to the a raised to the b, that's x to the a times b. This is where we multiply the powers. And if we look at why this is the case because of the definition of multiplication. Let's again look at an example. Suppose I had x squared cubed. What does this mean? It means x squared times x squared times x squared. So if we go back to the previous rule, my exponent would be 2 plus 2 plus 2. I'm adding 2 to itself 3 times. That's the definition of multiplication, 2 times 3. So that's why this particular guy is multiplication. The next rule we want to look at is the power over a product rule. And this rule says if I have x times y all to the a power, then I could take the x to the a and the y to the a. And the reason for this one is because multiplication is commutative. So what if I had x times y cubed? This is xy, xy, xy. But multiplication is commutative. I can do it in any order I want. So I could put all the x's up front, all the y's in the back, and that makes it clear that I've got 3 x's and 3 y's. That's why that rule works. The next rule is the power over a quotient rule. And so this rule says if I have x over y to the a, that's x to the a over y to the a. And that's another hopefully pretty obvious one. If we had x to the y cubed, that's x over y, x over y, x over y. The way that we multiply fractions is to multiply the tops, then multiply the bottoms, and you can see that you get x cubed over x cubed, or over y cubed rather. The next rule is the quotient rule. This rule says if I have x to the b over x to the a, that's x to the b minus a. I subtract the powers. And the reason for this comes about from how we divide common factors. If I had x to the fifth over x squared, that would be xx, x, 5x's, over xx. Well, one of them would divide out there, another one would divide out there, and I'm left with three of them. So what happened? Each one on the bottom divided out with one of them in the top. So if I'm talking about that in terms of counting how many are left, each one in the bottom took one of the top ones away and subtracted them. So that's why we have our quotient rule. The next rule we want to talk about is the zero exponent rule. This is the rule that says anything to the zero power is 1 as long as x isn't 0. 0 to the 0 is undefined, and we'll see why that's the case when we look at why this works. The reason this works is to say, what if I had x to the fourth over x to the fourth? Well, if I do my whole subtraction rule over there, the quotient rule, this is x to the 4 minus 4, which is x to the 0. But anything over itself is 1. So that tells me x to the 0 must be the same thing as 1. Now this wouldn't have worked if x were 0, because if x were 0, I'd be dividing by 0, and that's not allowed. So that's why x to the 0 is always 1. There's also a little bit deeper reason why, that 0 says it's our starting point for multiplication. We haven't multiplied by any x's yet if I have x to the 0 power. Your starting point for multiplication is always 1. You do 1 times whatever comes next times whatever comes next. The last rule is the negative exponent rule, that if I have x to the negative a, that's 1 over x to the a. We basically already talked about this one, but we could also look at this one in terms of our quotient rule to say if I have x to the 0 over x to the a, and I subtract those exponents, 0 minus a would be negative a. But x to the 0, remember, is 1. So that's 1 over x to the a. So that shows that x to the negative a is the same thing as 1 over x to the a. So those are all of your rules of exponents. I want to make sure you wrote them down in your notes because we will be applying them. And I want to make sure you know where they come from, so that if you forget one, you can always figure it out on your own. So in this example, we're going to follow the directions of use the properties of exponents to simplify and write results with only positive exponents. Again, start a new flashcard. Now, when we're using the properties of exponents to simplify, one of the things I want to point out here is that this is nothing new to this course at all. All you're doing is the exact same thing you did in your previous math course as far as using properties of exponents. Now, these exponents are fractions, sure, but we're not even using the fact that they're fractions. We're just going to simplify these down using the same rules as you used in your previous math course. Now, please note, though, that your answer does need to have positive exponents. So if you end up with a negative exponent for some reason, you're going to rewrite it as a positive one using the rules. So the first rule here, we have b to a power times b to a power. We're supposed to add those powers together. So that's 1/3 plus 5/3. If we add those together, we get 6/3. 6/3 is 2. B squared. That's it. We didn't do anything with radicals. We're just using properties of exponents. On this next example, we have 7 to a power over 7 to a power. We can have a base that's a number, and that's perfectly fine. Our rule here is that we're going to subtract the powers. 1/3 minus 4/3 is negative 3/3 or negative 1. But instead of a negative exponent, we're going to rewrite this. A negative exponent means to take the reciprocal of the base. And there's our answer for that one. Now the next one gets a little bit tricky. We've got a lot going on in this one, but let's take it one step at a time. The first thing that's going on is in the top, we've got this parenthesis with an exponent. So if we use a power over a product rule, this tells me take that fifth power to the number, to the x, and to the y. Now before I simplify anything, I'm going to just literally write that. I'm going to write 2 to the fifth, x to the 2/5 to the fifth, y to the negative 1/3 to the fifth. Now because I'm dealing with rules of exponents, I'm going to go ahead and also put a 1 onto that y, just to remind myself that it's y to the first. Now one of the things I just want to point out about this is start writing stuff down. There's going to be some intimidating looking problems at different points, like the one that we're doing right now. Take it one step at a time and just write stuff down, one step at a time. So now up top, we're going to simplify this a little bit. We have 2 to the fifth, that's 32. Then I'm going to look at my x's. When I raise a power to a power, I multiply the powers. That's one of my rules. If I'm multiplying 2/5 times 5, I just get 2. So that's x squared. Similarly for the y, I'm going to multiply the exponents. Negative 1/3 times 5 gets me negative 5/3. I'm going to copy down these guys. So now I need to simplify this fraction. And what I would do if I were you in problems like this is I would break this up into basically 3 separate problems. The numbers, the x's, and then the y's. Looking at just the numbers, I've got a 32 on the top. Nothing to simplify, he's just going to copy down to the next step, a 32. If I look at the x's, I have x squared over x squared. That's 1. They divide out. Now let's look at the y's. I have y to a power divided by y to a power. So I know I'm supposed to subtract those powers. I'm supposed to subtract negative 5/3 minus 1. In order to do that subtraction, I would need a common denominator. So I'm going to rewrite 1 as 3/3. Now if I have negative 5 minus 3, that's negative 8/3. So that's what I'm getting for my y's is y to the negative 8/3. Now we don't need to write the times 1 in our final answer, but we're also not allowed to leave a negative exponent. The 32 stays in the top because he doesn't have a negative exponent. But the y does have a negative exponent. So we're going to put him in the bottom. He's still 8/3. Remember that we're taking the reciprocal of the base of the y. The y is what gets moved down to the bottom. The 8/3 stays as is. And that is our answer. All right, we have a new set of directions. New flashcard for you. Directions here are use rational exponents to simplify. Assume that variables represent positive numbers. So the fact that we're told to assume that variables represent positive numbers, remember this means we don't have to worry about absolute value bars. But more importantly, let's look at the first sentence of the directions. Use rational exponents to simplify. That's basically 2 steps. And so we need to understand what that terminology means so that we understand what those 2 steps are. Use rational exponents. Rational. The first 5 letters of rational are ratio. Ratios are fractions. So this is saying use fraction exponents. Then simplify it. So it's giving you 2 steps. The first step is let's use rational exponents. So the first step of this first problem is to say my power is 4. My index is 8. So I'm going to write this as x to the 4/8. Now let's simplify. 4/8 simplifies down to 1/2. Now this is a little bit tricky on how we want to write our final answer, and this is why it's important to make these flashcards. In this problem here, the directions said use rational exponents to simplify. So our final answer should be rational exponents. So I'm going to leave my answer like this. Whereas we know this is equivalent to square root x, that's not what we were asked for. We weren't asked to rewrite this as a radical. We are told to use rational exponents, so it makes more sense to leave our answer as x to the 1/2. Now for the second example, there's a general rule that's important, and you'll notice in your notes that's at the bottom of this example. Whenever there's a number that can be written as an exponent, do so. So the first thing I'm going to do before I even follow my directions on this problem is I'm going to rewrite 25 as 5 squared. Once I do that, then I say my power is 2, my index is 6, so this is 5 to the 2/6. Then I simplify. 2/6 simplifies to 1/3. And that's what I'm looking for. Now this last one's a little bit tricky. I'm taking the 4th root of that whole thing. So if I'm using rational exponents, then what this is saying is to take x squared y to the 6th and raise that whole thing to the 1/4 power. Then I can use the power over a product rule that says take my x squared and raise that to the 1/4 power, and take my y to the 6th and raise that to the 1/4 power. Now I'm raising a power to a power, so I multiply the powers. Then I can simplify. 2/4 simplifies to 1/2. 6/4 simplifies to 3/2. And there's the answer I'm looking for. Now for this example, I want you to notice how the directions are different than our previous example. These directions, new flashcard, say use rational exponents to write as a single radical. So we're using rational exponents. So our first step stays the same. It's to say take whatever radicals you see and rewrite them as fraction exponents. But then it's saying whatever you get in the end, after you simplify stuff down, your final answer should only have a single radical sign left. That's our actual goal of this problem. So let's take the first example, and let's rewrite each of those radicals as a fraction exponent. The square root we can rewrite as the 1/2 power. The 4th root we can rewrite as the 1/4 power. Now I have x to a power times x to a power, so I know the rule here is that I can add those powers together. And so off to the side in my scrap paper land, if I add 1/2 and 1/4 together, I need a common denominator. So I know that's going to be 2/4 plus 1/4, or 3/4. So I get x to the 3/4. But again, my directions here were to write as a single radical. So my final answer should be a radical. So I'm going to take this x to the 3/4 and say, hey, this power of 3/4, 3 is the power I'm raising to, 4 is the index. So I have an index of 4, a power of 3. And that's the answer that I'm looking for. Let's come over to this guy. This guy's a little bit trickier. Directions are still going to help us though. Because let's start off with the first part of the directions that say to use rational exponents. The cube root means the 1/3 power. The square root means the 1/2 power. Now we can't simply add these exponents together because our bases aren't the same. So that's not the rule of exponents that I can use. So instead, I really got to take a step back here for a minute and say, what was my final goal again? My final goal was to write a single radical. What part of the exponent is that referring to then? That means in the exponent, I'm looking to say I need the same denominator. In order to have a single radical, I need the same index. So I need the same denominator in both of these. So we're going to try to rewrite each of these fraction exponents with the same denominator. We're going to rewrite 1/3 as 2/6. We're going to rewrite 1/2 as 3/6. And now comes a step that we haven't done yet, even though it's perfectly legal, is we're going to take that denominator of 1/6 and we're going to apply the power over a product rule in reverse. Remember, the power over a product rule is the one that says if I have xy to the a power, then that's x to the a, y to the a. And we usually go from left to right with this rule. We usually take the a power to each. But this rule could go right to left as well. That if you have a product of two exponents that both have the same power, you could pull that power out. And that's what we're going to do here, is we're going to say 3 squared times 2 cubed. I can pull the 1/6 power out. 3 squared is 9. 2 cubed is 8. And 9 times 8 is 72. So I'm looking at the 6th root of 72. Now I have a single radical. That was my goal.